Okay, this is another try at getting a video recording of lesson 9.3 or chapter 9, lesson 3, and this should be part 3 of 3, and this topic is exponential increase and decay. We'll be learning how to use equations that use an exponential equation. So in the scheme of things, this is where we're at, item number 3. And let's first talk about interest terminology. This is when you invest money, or maybe you are paying a debt. And simple interest is interest that is added once at the very end of the investment period. Compound interest is interest that it's calculated at specific intervals, like monthly or quarterly or maybe semi-annually or even just annually. And it's added to the principal. The principal is the amount of money you started with. I'm going to have a sheet with all this terminology in it in a little bit. And anyway, so with compound interest, you calculate interest at specific intervals, and then later the interest is calculated on this larger amount because you'll add this interest in at a compounding interval, and then your interest, the next compounding interval, your interest is earning money on that larger amount of principal. Here is the simple interest formula. A simple interest problem would be like you borrow $500 from Uncle Joe, and you're going to pay him back in 2 years, and he's going to charge you 5% interest, but he's not going to charge you any interest until it's time to pay the loan back. So the amount you started with, the amount at the end that you have to pay back is equal to the amount you started with plus the interest rate times the principal times the number of years that your loan is out. Now, because p is in two places in this equation, we can factor out the p and have this equation: a is equal to the amount at the end is equal to the amount at the beginning times that quantity 1 plus the interest rate times the time. Now the interest rate will be as a decimal and not as a percent. So remember to make that transformation when you use that in this formula. Let's do an example. This is compounded yearly $100 at 5%. So at the end of the year 1, what's money is in your account is $100 plus 5% of $100. In year 2, you start with that amount of money, and then you will add 5% onto that amount of money. This is now compounded yearly. Well, here's another way to say what's the way the formula works. So you start with your principal, you add 5% onto your principal. Because p is in both places, we're going to factor out the p, so it's p times 1 plus the interest rate. You could condense that to 1.05, but I'm going to keep that separate because this is how we're going to develop that formula no matter what the interest rate is. At the end of year 2, you start with what's at the end of year 1, and you add 5% onto it. So because this chunk is the same in that term and that term, we factor that chunk out. That chunk times 1 gives me that piece. That chunk times 0.05 gives me that piece. So this is you'll notice that we really just have 3 factors here. P is a factor, 1 plus 0.05 is a factor, 1 plus 0.05 is a factor. So, over a bunch of years, the part that's going to change is how many times you multiply by this 1 plus 0.05. So, in year t, maybe year 5 or year 10, the part that's going to change is this exponent, and it will be 5 for 5 years and 10 for 10 years. That, by the way, is interest compounded yearly. Let's talk about interest compounded at spaces smaller than a year, but maybe with 5% interest, and that would be calculated as 5% per year, not per compounding interval. For example, let's say that money is, or a loan is, or a bank account or a savings deposit account is got a steady amount of money in it, and it's going to be compounded. It's going to earn interest at intervals, for instance, monthly. So at the end of month 1, if you invested $100, then you take that 5% yearly interest, divide it by 12, and then multiply that to the $100. So that's what's going to get added onto the account. So that equals, and because this 100 is in both places, that is equal to 100 times 1 plus the interest amount. The interest now is 5% divided by 12. And I factored the 100 out because 100 was here and 100 is here. 100 times 1 is 100. 100 times that interest chunk is this expression right here. Okay, in month 2, you're going to start with this amount. It's a little bit more than $100. And you're going to add 5% onto that little bit more than $100. So another way to say this, notice that I have taken this chunk. It's here and it's here. It's in this term and it's in this term. So I factored it out. So that chunk times 1 equals that piece right there. And that chunk times the interest rate equals that piece right there. Well, again, you notice that the piece that's the same is the 1 plus 0.05, and this is multiplied to that, and that's multiplied to this. Because those are all factors, I can write the interest portion as that with an exponent on it. So that's the amount that's the end of month 2. So since we're going to do this 12 times in a year, then that exponent becomes 12. And then if we also tell this formula how many years we're going to do it, then this becomes our compound interest formula. So the amount at the end is A. The amount at the beginning is P. We call that principal. And 1 plus our interest rate. This is why I wanted to keep this separate and not roll it into one decimal. 1 plus the rate of interest, this will be as a decimal, divided by the number of compoundings in a year, all of that raised to the power nt. So this number of compoundings is going to get done that many times, so n here and n here, and then you can multiply it out times the number of years. So when you put something like this on your calculator, $100, 5% interest, compounded monthly, then this is what it's going to look like on your calculator. Parentheses around the exponent parts, this is n and that's t, are extremely important. This is the common error that's made when people go to put this on their calculator and figure out how much money there's going to be at the end. Here's example number 5. Find the amount owed at the end of 5 years if $1,600 is loaned at a rate of 9% compounded monthly. Let's move this over to my board so you can see it, because you probably can't see it on there. Here's our interest compounded formula. A is equal to P 1 plus R over N raised to the NT power. And A is the amount at the end. The amount we started with was $1,600. And it was going to be for 5 years. And at 9% interest and compounded monthly, 12 times yearly. All right, we just plug all this stuff into that formula right there and then pick up our calculator. So A, the amount at the end, is going to be $1,600. 1 plus, our interest rate is 9%. We're going to put it on as 0.09. 12 times a year, so 12 goes down there. We're going to do that 12 times per year, and we're going to do that for 5 years. Now just get in the habit of putting that in parentheses, and I think that will help you remember to put it in parentheses when it's on your calculator as well. So let me show you how this enters onto the calculator. And here's my calculator. Yeah, okay, I think you can see that. So we can get the whole thing on at one time, 1,600, and a start parenthesis, 1 plus, now you don't have to wrap parentheses around your fraction, 0.09, because your calculator understands the order of operations within that parentheses. And then raised to, and here's the other really important parentheses, 5 times 12, or 12 times 5. And press enter. So the money that you have at the end is $2,505.09, round to the nearest cent. Okay, here's that promised list of terminology. If you download the lecture notes, this list is in that lecture notes. You might want to have this in your notes for your test, but it also might be something after you've done a little bit, then you understand how that works. So P is the amount of interest at the beginning, and this is the this is the amount of money at the beginning, and this is the amount of money at the end. R is the interest rate as a decimal. Remember to transform it to a decimal. The time invested, typically in years for this formula, is up here. The number of times the interest is compounded in a unit of time, and that would be years in most of our applications, is going to be N. Now, N. Let's talk about N a little bit here. If it is compounded yearly, then 1 time per year, N is 1. If it's compounded semi-annually, that means every 6 months, so N is 2. If it's compounded quarterly, 1 quarter is 4. It means 4 times a year, every quarter. If it's compounded monthly, there are 12 months in a year. And if it's compounded daily, we use 365, even if it's a leap year. And I just did example number 5. My slides were out of order, so that's example number 5 right there. There is a problem from exponential decay. That would be this page right here. And sometimes the formula looks a little bit different. We have amount at the beginning, amount at the end. Then this part with the r, with b raised to the negative r, means that we're going to be decaying, because r will be a positive number, but we're going to be taking a little bit out every time. So the rate of decay is r, and then when you put it into the formula, it becomes negative r. Usually it's a percentage. It might just be a number that they give you in the book. The negative sign causes the end amount to decrease rather than increase. The time required may not be years. It might be minutes. It might be seconds. So pay attention to that one. Here is a problem involving radioactive decay. This is 9.3, example number 6. As a result of a nuclear accident, radioactive debris was carried through the atmosphere. One immediate concern was the impact the debris had on the milk supply. This scenario was probably Chernobyl, which was in January of 1986. The percent Y of radioactive material in raw milk after T days is estimated by this formula. And 100, this might be a percentage. So if we call the amount measured at one point in time, then we're looking for, this is percent of radioactive material in the milk after 30 days. So all we really want to do is plug in 30 for T, because notice that the time here is T days. So let me set this formula up here again, and you can see how it works. Y equals 100, 2.7 raised to the 0.1 t. I think it means it's falling by, falling by perhaps 10% per day, which is a pretty quick drop off for radioactive material. So what we want to do is plug in 30 for t after 30 days. And so you'll pick up your calculator. And let's see if we can kind of show that off to one side. 100. 2.7 raised 2. Now I didn't put that in parentheses on the board, but you'll definitely want to do it on your calculator. Negative 0.1 times 30. Okay, that's not showing up very well here. And nope, just not going to show up very well. When I press enter, I get 5. So after 30 days, there's still, I believe what this means is that there's still 5% of the radioactivity that there was when we first began to measure the amount of radioactivity in the milk. So we say approximately equal to 5.08. And I'm saying 5% because that was 100, so that's probably 100%. That's our baseline measurement for the amount of radioactivity in the milk. Doesn't mean the milk's still poisonous, doesn't mean the milk was poisonous right there. It just means in 30 days that there's only 5% of the radioactivity that there was at the beginning.